whereas we have so many examples of modern day structures built with modern technology, modern materials, but yet they deteriorate, they do not see a good lifespan, and we see snags, even failures in extreme cases. We had concrete come up, and then we had the invention of RCC, and this became the go-to material. And therefore, even buildings that were built in, say, the 20s or 30s, 1920s to 30s, even those buildings which are still standing, they exhibit a very different quality from what we see right now. And even, in fact, the ones a little later, you can say the 80s or 90s, versus what is right now. Mr. Kunte, have you ever been on a heritage walk, which have become so popular right now, and gone to any historic precinct of any city in India and seen and admired those old buildings which have been standing for centuries? They're made of brick or wood or timber, so traditional materials, and they've been standing there for so long. And even other kind of buildings which are, say, 80 years old, 70 years old, that we look around, because we are in this profession of construction, so we obviously notice. And these buildings are even so performing so well even right now, in fact, when it comes to adaptive reuse or retrofitting and things like that. So that got us thinking that what should be the life of a structure for its optimum use, and even thinking about a whole host of factors. So we thought that at CQRA Quality Dialogues, that would be a very
appropriate topic. Yes.
exactly, yes. So welcome to CQRA Quality Dialogues. It will be a wonderful talk, I'm sure, again, to get together and discuss something on CQRA Quality Dialogues. And I welcome all our viewers as well to this another wonderful episode. I hope you've had a very good sort of insight on a lot of subjects that we have been trying to cover. And CQRA Quality Dialogues is where we talk about the quality aspects of construction in terms of its materials, its processes, and its tools. And we have the expert himself, Mr. Ujwal Kunte, to decode quality for us. And Mr. Kunte, as you all know, is the founder and MD of CQRA, which is one of the country's leading auditors for construction quality, safety, and QS. So, Mr. Kunte, looking forward to this wonderful session.
Yes, thank you.
Right. So, we just spoke about these, historical buildings, great Mughal structures that we sort of go any time we, visit touristy place, or these Rajasthani palaces, traditional timber work of houses in Kerala or Kashmir or anywhere around the country, steel structures. Then there are buildings which sort of are still standing today in terms of, New York skyscrapers. And I could just keep on talking about so many of them. So, the basic question is, why are these structures still standing? They're still worthy of use even now. Whereas we have so many examples of modern day structures built with modern technology, modern materials, but yet they deteriorate. They do not see a good lifespan, and we see snags, even failures in extreme cases. So, just help us decode that bit.
So, all these wonderful structures, including, Taj or many of the forts that we see,
Right.
they are built of materials that are quite eternal. The stone,
Okay.
they have used lime, as a mortar, then
True.
bricks or sometimes timber.
Mm-hmm.
So these materials have essentially a very long life. There is nothing that deteriorates them. And all these structures that were built, they were primarily built as compression elements.
Okay.
Most of the old buildings you will see, or they had dome like structures, okay, or arches,
Right.
or
Yes.
columns.
Mhm.
So they were primarily in compression, okay,
Okay.
very less flexion and tension. So today,
Mm.
the modern day buildings, we are having sleek, tall buildings which
Right.
are having a lot of flexure and tension elements. So basically, when you have tension elements, you have to bring in metal, so
Okay.
steel.
Right.
And
Okay.
when you bring in steel,
Mhm.
that is the material that deteriorates.
Mhm.
In earlier days, whenever they used any metal, that used to be a non-ferrous metal. in Vedic concepts, you are not supposed to use any ferrous alloy in the construction.
Okay, that's.
So that was the
Mhm.
concept, because the copper will, they used to use copper strips to interlock blocks.
Yes, yes.
That's what they have done in the Ram temple also.
Okay.
So basically, these materials, were not corroding. But when in modern day construction, when we use rebars for taking tension,
Mhm.
which is primarily made of steel,
Right.
steel is a material that deteriorates over time.
Okay.
Okay, whenever
Yes.
there's a moisture and air, it starts corroding,
Right.
and then it expands, and then it
Mhm.
also deteriorates the concrete that is surrounding it.
Okay.
So
Yes.
that's the process of corrosion and deterioration.
All
So
right.
primarily, all the new RCC buildings,
Mhm.
because they have steel in it, they come with a expiry date.
Okay, that's kind of an interesting thing to note, which I'm sure a lot of lay people don't know about this, and
Correct.
it was, you know,
True.
an interesting insight. So, okay, these were historical structures which used different kind of materials built in different times for probably different uses. But, as technology improved or kind of got advanced in terms of construction, we had concrete come up, and then we had the invention of RCC, and this became the go-to material. And therefore, even buildings that were built in, say, the 20s or 30s, 1920s to 30s, even those buildings which are still standing, they exhibit a very different quality from what we see right now. And even, in fact, the ones a little later, you can say the 80s or 90s, versus what is right now. So, again, how do we draw that comparison? How do they differ from what is happening right now?
A very valid point. If you go along Nariman Point, the
Mm.
Maker Chamber buildings, or many of the old RCC structures are still standing without any
Right.
problems. There's a classic case where in VZTI, the old hostel building
Mhm.
RCC was still okay, but the newer building which was constructed much later needed repairs, retrofitting.
Okay.
So a lot of people wonder why is with new modern
Mhm.
materials we are not getting the required life of the building. So here this is a very interesting topic, a little bit of technical.
Right.
In earlier times they used to have very low grade of cement. Okay,
Okay.
so grade of cement signifies the strength of cement.
Right.
Okay,
Yes.
so to get that required strength,
Mhm.
they had to use a very stiff concrete. Very
Okay.
they had to use very low water cement ratios, because
All
if they
right.
used high water cement ratios,
Mhm.
then they would not get the required
I
strength,
see.
because
Okay.
cement inherently was of that quality.
Right.
Now
Okay.
over the years what has happened is cement quality has improved because of the technological advances.
Yes.
The strengths have more than doubled.
Mhm.
Okay,
Okay.
what it means is that even if you have a little higher water cement ratio, you
Okay.
still get the strength.
All
Okay,
right. Okay.
and plus the requirements have also changed. You have got very thin elements with a lot of rebars,
Mhm.
so
Yes.
you need a very very workable or liquid consistency of concrete.
Okay.
So there's a very high risk of putting excess water inside the concrete, so
All
which
right.
makes the concrete structures porous. So
Okay.
you need a very good quality control. Of course there are modern day
Mm.
admixtures that are available, which can give you that consistency.
Right.
But if you
Yes.
don't have quality control processes on site,
Mhm.
and if you don't use proper materials, then there's a high risk of making a very porous concrete.
Okay.
Okay,
Right.
secondly, in those days they were using mild steel,
Yes.
and
Okay.
now we are
Mm.
having Fe415 and Fe500. So generally it is known that Fe415 and 500 are more prone to corrosion compared to mild steel.
Okay.
Plus there's another angle to it, that the elastic modulus of all these materials is the same. What
Mm.
it means
Yes.
is that when Fe415 or Fe500
Mhm.
steel you are using,
Yeah.
it will undergo a higher elongation, you know
Okay. Okay.
to achieve that particular strength, which means that these structures using
Mm.
Fe415 or 500 are
Okay.
likely to crack little more than what it was in the earlier stages.
I see.
So
Okay.
when you have this, when you don't have,
Mhm.
and then curing, most important.
Right. Okay.
People were very conscious about curing the structures, and the
Mm.
construction used to happen in a very slow manner.
Yes. Yeah.
Now, you have these 10 days, 12 days slab cycles,
Hmm.
and people are not able to give adequate attention to curing. So
Okay.
all these conditions together,
Mm.
result in structures where, corrosion can happen quite fast.
Right.
And
Okay.
that's why you have problems in many of the buildings.
Okay, so these are actually very serious issues, and the engineers or site managers really need to kind of manage processes. Like you said,
Correct.
quality becomes really important in these
True.
cases. And of course, now concrete with, or cement rather, with easy availability and the plastic quality of concrete, it's become a ubiquitous material. We see it everywhere, and there is ease of use, of course. And when you come to RCC also, it is something that is readily available for us to use. So how does my question is basically, how does RCC fare when you compare it with traditional materials like there is steel, there is timber, there is stone, wood, or even earth, for that matter, which are again still in use in some parts of the world, and they fare very well.
See, RCC is inevitable. The
Hmm.
scale and the speed of construction that you're having, and
Right.
the tall buildings that you're
Hmm.
having, you cannot have them in any other material other than RCC. The
Right.
only
Okay.
option is steel.
Okay.
And there have been tall steel buildings that have been constructed world over,
Hmm.
and it's a viable option. But again, there is a problem of fire, resistance.
Right.
Now,
Yes.
we know what happened in 9/11. How that particular fire brought down the entire,
Right. Yes.
World Trade
Yes.
Center.
Yes.
You know, so there is a risk of fire, and
Hmm.
they are more expensive traditionally.
Okay.
So RCC is going to be inevitable, and
Okay.
as far as, because we are putting steel inside,
Hmm.
we have to be very, very careful on the controlling the quality of concrete, the quality of the concrete and the cover
Okay.
that offers protection to the steel.
Right.
Because once the corrosion starts in, steel, it is
Hmm.
like cancer. You cannot,
Yes.
the method of, undoing it is either not there, or it is very, very expensive. There
Right.
are certain
Yes.
modern techniques that have come up,
Yes.
but they are very, very expensive, and they can only enhance the life of the structure, but not give it that kind of, long life.
Life.
So I would say that RCC is inevitable.
Hmm.
It is more economical. You can't use these other materials for large scale construction,
Right.
so we have to deal with it.
Okay, so that's the sort of bottom line, that you have to deal and manage this
Manage.
kind of construction process. So I'm coming to the question that we are finally asking: that what is the ideal life, or what should be the life of buildings? And like as you mentioned about the Ram Temple as well, that it's built to last really long, for 1,000 years, and therefore it does not use metal in any way. So can you kind of shed light on this, that how do we kind of maximize the life, or even what should the ideal life of a building be?
Yeah, actually, you mentioned about Ram
Mm-hmm.
Temple. They have not used rebars,
Hmm.
steel rebars. They
Right.
use copper, clamps,
Okay.
between different blocks.
Okay,
So
they've
which
used
will not.
copper.
So
Hmm.
the design life is 1,000 years.
Okay.
So see, world over, there are structures that have been designed for very long life. Like if you go to
Hmm.
Netherlands, they have captured a portion of land. But it's they are having shortage of land, so they
Yeah.
wanted to reclaim some of the land along the seashore. So
Right.
they built structures known as dikes.
Yes.
So they have built these concrete dikes
Hmm.
for a life of 400 years, design life of 400 years.
Okay.
So you can design a concrete building with a very long life,
Hmm.
but ordinary structures that we live in, the residential buildings,
Right. Yes.
they are normally, the life is between 50
Hmm.
to 75 years.
Okay.
If it is a good, if you take all the good quality control measures,
Right.
you can easily get a life of 75 plus years.
Okay.
Okay, but
Hmm.
the way modern buildings are being built today, the speed of construction, the control on the water cement ratio,
Yeah.
the way the curing practices are
Hmm.
being implemented. So many of the buildings will start showing, signs that they need repairs within 30 years.
Okay.
So ideally it should be 50 to 75 years, but you can have problems in 25 to 30 years if you don't maintain the quality.
Okay. So it all boils down to the quality processes
Yeah, yeah.
as such. Um, so there should be a method to assess the life of a building, right? Are there any models or any kind of a process that people can refer to or look at to know and kind of to understand how this life of a building should be?
Yeah, actually, a lot of advancements have taken in this
Hmm.
aspect. A lot
Right.
of models have been developed across the world. Of
Okay.
course, some are empirical models. Some are based on stochastic, probability
Okay.
theory. But what they essentially do is
Hmm.
that they look at the degradation, process.
Right. Okay.
So primarily affecting the rebars. Okay.
Okay. Yes.
So I mentioned that there are certain things that affect the rebars. So that is
That's right.
corrosion.
Okay.
Now, when does corrosion happen? When normally concrete is alkaline. You know, the
Right.
pH of
Yes.
concrete is almost 14.
Hmm.
So in alkaline environment offers a natural protection to steel. So it kind
Okay.
of prevents it from early rusting.
Right.
But there's a carbonation process. So
Mm.
there's a lot of carbon dioxide in the atmosphere. So that
Right. Yes.
carbon dioxide interacts with
Mm.
concrete, and the carbonation happens where
Right.
the alkalinity of the steel in the cover zone drops, and there it becomes potential corrosion can start,
Okay.
or there could be chloride penetration. All these models, they look at these degradation processes, how chloride ions will penetrate or diffuse inside the concrete,
Hmm.
and based on that it is possible to predict what would be the residual life of a building.
Okay.
Okay, so all these models, there are different models. You have to look at the quality of the cover, the thickness of the cover, the quality of the concrete. Then you have to do some testing on the concrete about, maybe you would be measuring chloride diffusion,
Okay.
permeability,
Mhm.
and based on that they will tell you that you have a balanced residual life of 25 years, 30 years, 40 years, all that. So it
Okay.
is possible.
I see. Okay. So that is something really encouraging that,
Yes.
one can kind of find out or assess basically what is the lifespan of the
Correct,
building.
correct.
This is what we spoke about on a, sort of very technical, in technical terms, in terms of, what is the materials and things like that. But there are other factors as well when it comes to life of buildings, like there are environmental as well. So you build a building so that, it lasts for a certain time, so that there's less impact on the environment, because any human activity is kind of, having some sort of negative impact in that sense. There are also other issues like when it comes to redevelopment. So not just to build something today, keeping redevelopment in mind after 30 years and trying to reap those profits, or which are supposedly going to kind of come after that time. So these are things which are happening in the building world today, that construction is happening for the purpose of profitability, or how much to maximize basically. So how can we, within that purview of these kind of factors, how do we kind of talk about the life of structures?
Good question. What happens is, if you look at, you mentioned about
Mhm.
redevelopment.
Right.
Now redevelopment primarily happens on two
Mhm.
counts. One is that people want modern buildings, modern amenities, and second is, in many cases the existing building is in ruins. It
Mm.
needs repairs.
Right.
Okay. Now, fortunately, what happens is that because of the current FSI regulation, and people get extra FSI, so the cost of reconstruction primarily gets covered, because of the availability of additional FSI.
Right. Yes.
Okay. So some of the buildings come up for redevelopment, within 30, 40 years
Mhm.
also. Okay.
Right.
But imagine if there was no FSI available. Okay,
Okay.
additional. Somewhere
Yes.
this process has to stop.
Right.
And you look at whether these people will be able to finance the cost of reconstruction.
Hmm.
Let's say a building which has no additional FSI, but it
Right.
is needs to be reconstructed because it is reached its point of deterioration, that
Right.
maximum
Yes.
limit
Yes.
where repair cost, you cannot retrofit it. So
Right.
it is so exorbitant for people who are staying there.
Hmm.
Imagine, even people have problems contributing to small repairs also in buildings.
That's true. Yes.
Okay. And when there is no incentive, but people have to pour money to
Mm.
reconstruction, you will find that very few buildings will get redeveloped in that case.
Right.
And
Yes.
after all, when we talk about carbon footprint also,
Hmm.
we should look at, imagine a building which you have constructed, you are demolishing that entire building and reconstructing a taller building. So
Right.
how much carbon footprint are we adding up?
Hmm.
So looking at all these aspects, it is wiser and better to get buildings designed for 50 or 75 years at least. You can even
Okay.
design buildings for 100 years,
Okay.
so that the option to reconstruct is not forced on the home buyers or
Right.
the residents. They can, it's a choice.
Okay.
So we should look at methods, and there are very good techniques available
Hmm.
to enhance the life of buildings, by using certain specific materials, designs,
Okay.
and taking certain precautions. You can
Mhm.
easily make it.
Right.
So it's always better to design buildings for long life.
Okay. That was actually wonderful and something like an eye opener as to what the situation could be if there is no incentive to redevelop. And that is something that we are actually facing a lot in the market. So we're going to hold that thought right now. And you mentioned enhancing the life of buildings. So in the next part of this session, where we are talking about the life of structures, we're going to talk about enhancing the life of buildings and how you can make the most out of all the investment that has gone into that particular construction. So stay tuned for the next part. Thank you.
Thank you.